Hey everyone, so today what we're doing is we're talking about a cold air standard Brayton cycle. Now first let's talk about what a Brayton cycle actually is. So we have an intake of just atmospheric air right here that goes through a compressor that compresses the air, of course, obviously because it's a compressor, big thoughts. And then we go from state 1 to state 2, it's the compressor. And then from 2 to 3, we have a combustion chamber. This is where the bulk of your heat is being added. This is just straight heat addition in process 2 to 3, which is, as I said, your combustion chamber. The next thing is we're going from process 3 to 4. And what we're hitting here is our turbine. That is where we're getting our power from. So something important to remember, the amount of work that we get out of the system net is going to be equal to the work we get out of the turbine minus the work that we have to put into the compressor. That's going to come in handy with our problem later. Now, before we go into our problem, let's also talk about our pressure-specific volume diagrams as well as our temperature and entropy diagrams. So our PV diagram and our TS diagram. We start around here at state 1. We kind of curve up to state 2. Then we have an isobaric process. Isobaric meaning that the pressure does not change from states 2 to 3. And then we come down here to state 4. And state 4 is where heat's getting rejected out. So anything left after the turbine is just getting exhausted out. And then now let's come over to our temperature and entropy diagram, TS diagram. Down here we have state 1. This is supposed to be state 2. So just ignore that. This is state 2. Grab my little expo marker. That's state 2. And then that's also an isentropic process. Now because we're assuming a cold air standard problem, that just means that this is the most idealized problem that we could have. So things like ideal gas law are taken as absolute truth. We get to use a few extra constants, which you'll see in our problem later. And also we get to assume that these actually are isentropic processes, meaning that the entropy does not change. In a real Brayton cycle, this would not be a perfectly isentropic process. And then we have to bring in some more formulas to find efficiency for the turbine and for the compressor at that point. But for our problem, for our purposes right now, we get to assume that entropy doesn't change between these 2 points. And then we have our heat addition from 2 to 3, which is this curve right here. And then we have another isentropic process again from 3 to 4, and then we go back to 1. So that's really all the background that you need to solve this problem. I'll give you all the formulas you need, I'll give you all the information you need, and we'll work through it together. Okay, so as I stated before, what we're working is a cold air standard Brayton cycle, which means we get to use a lot of formulas that you don't get to use if you're assuming variable specific heat. Now, while variable specific heat is a lot closer to what reality actually is, cold air standard is still a decent approximation, and also it helps you to figure out what's going on in the cycle, how efficient it might be, and it's just very idealized, but it helps you learn a lot better because it's just easier. So what we're given in our problem statement is we're given our pressure ratio. What your pressure ratio is nothing more than just pressure 2 over pressure 1 and pressure 3 over pressure 4. If you think back to our PV diagram, processes 2 to 3 and 1 to 4 were all isobaric, which means the pressure didn't change. So this pressure ratio is equal to just P2 over P1 as well as P3 over P4. We'll use that quite a bit. The next piece of information that we're given is T1 equals 400 degrees Kelvin, that's pretty self-explanatory, as well as T3, which equals to 1300 Kelvin. You'll notice that we're working in SI units in this problem. Now, our first enthalpy that we're given is equal to 400.98 kilojoules per kilogram. Our H3 is equal to 1395.97, so 1395.97 kilojoules per kilogram. And then something that isn't specifically given in the problem statement, but we know is K. K is just a constant that we use in cold air standard problems, and it is always equal to 1.4. Okay, so that's all we're given. And you'll notice that we're given opposite ends of the cycle on our diagrams. We're given 0.1 and 0.3. So we're given the two kind of ends, if you will. Now, what we need to do is in part A, we need to find what the temperature of 4 is in Kelvin. And then for part B, what we're going to do is we're going to find the work net for the system per unit mass, specifically in kilojoules per kilogram. Now, kilojoules is a big unit, so that's just going to show how powerful these cycles can really be. And then finally for part C, which is going to be the easiest part, is just going to be finding the thermal efficiency, and I'll show you a trick to find that pretty easily. Now, the first thing that we want to do, of course, is part A. All right, find T4 in Kelvin. Okay, pretty simple here. What we're going to do is, since we're working a cold air standard problem, we're going to use our cold air standard formulas. Shocker. So the formula that we're going to use for that is T2 over T1 equal to P2 over P1. All of that is raised to the K minus 1 over K. So, you might be saying, aren't we trying to find T4? And yes, we are. Just like I said before, a lot of this stuff is interchangeable since we're assuming that this is an ideal system. So, this same ratio can be written as T3 over T4 equal to P3 over P4 raised to the K minus 1 over K. So, pretty cool, right? We just figured out how to change this formula and apply it to what we want to know. This is our known, we know this, and you might be saying, we don't know that, but we do. That's P3 over P4. That is our pressure ratio for our system across our turbine and across our compressor. So now we know this because that is equal to RP, this P3 over P4. We know what K is, we know what T3 is. Now all we need to do is we need to solve the system for T4. So that's just T4 is equal to T3 divided by RP, which is our pressure ratio, to the K minus 1 over K. That's an exponent, just to be clear. Okay, so this is not that hard of a formula, thankfully. So that's just T4 is equal to 1300 Kelvin over 6, which is our pressure ratio again, raised to the K minus 1. So that's 1.4 minus 1, that's 0.4 over 1.4. Now, after you plug that into your calculator, you should get something along the lines of T4 equal. So, after you plug that into your calculator, you should get something along the lines of 739 Kelvin. Okay, so we went from our base formula, applied it to our situation, we solved for the variable that we didn't know, and we got our answer, which is equal T4 equal to 739 Kelvin. Now next up is going to be part B. So the next part that we're going into is part B, which is find work net per unit mass. It's important because if we were just doing work net, we would have to find the mass of the system, which would be extremely hard, but we don't have to find that. We just have to find work net per unit mass. That's in units of kilojoules per kilogram. Now this part is going to be the hardest part of the problem, but I promise it's just a bunch of formulas, and that's it. There's nothing really that hard to it. It's just a lot, okay? So it's just a lot to remember. It's not that hard, I promise. So before we get to go into what work net is actually equal to, we need to find just a few more things. The first thing that we need to find is this little thing called CP. CP is nothing more than a constant of pressure for a cold air standard problem. Now you can remember that problem to problem if you really want to. Now I know that is equal to 1.0045 kilojoules per kilogram degree Kelvin. That's kilojoules over kilograms Kelvin. Okay, I just know that. But if for some reason you were to forget that constant, you can use this formula, which is K minus 1 over K equal to R over CP. Okay? You can use that formula because we know R, that's from our ideal gas law, that's our ideal gas constant, which is equal to 0.287 kilojoules per kilogram degree Kelvin, which you see the same units here. And then we know K is equal to 1.4 because it's the same for all cold air standard problems. So you can find CP that way if for some reason you've forgotten it, but you do somehow remember that formula or you're given that formula. So now that we know that, what we need to do is we need to find what T2 is. So what we're going to do is we're going to use the same formula that we used earlier, which is T2 over T1 equal to our pressure ratio raised to K minus 1 over K. Now this is actually easier than before because the thing that we're looking for, T2, is on the top. We just got to move T1 to this side. And I'm not going to do that. I'm just going to tell you what the answer is. You can do it on your own and see if you get the same answer that I got, which is 667 Kelvin. Okay, so that's what we needed to find before we got started. So now we get it to actually find what the work net per unit mass is in the system. So we're going to use the super cool formula. Work net is equal to the work of the turbine minus the work of the compressor, just like I said in the beginning of the video. Now we need to relate these two things to numbers that we have or can find, which is that's just going to be equal to mass times H3 minus H4, and that's in parentheses right there, minus H2 minus H1. Now, if you ever forget which enthalpies you need to use where, you can remember that 3 and 4 are together and 1 and 2 are together, and you're subtracting from the bigger number. So H3 is bigger than H4, which means you're going to subtract H4 from H3. H2 is bigger than H1, which means you're going to subtract H1 from H2. Now, we have our general formula, and we're just going to move mass under here. So work net per unit mass, which is what we want to get, is equal to H3 minus H4. That's in parentheses there still, minus H2 minus H1. The only thing that you really have to be careful with this part of the problem is your parentheses. Do not mess those up, because then that's going to mess up your entire problem. If you just decide to get rid of the parentheses, you're going to get a different answer. So please, please, please be careful with your parentheses. Finally, what we're going to do is we need to find H4 and H2. Okay, so how do we go about doing that? Well, we have to bring in yet another formula. I know, we're using them all the time here. So that formula is H2 minus H1 is equal to CP T2 minus T1. You see why we found CP and T2. So we know H1, we're trying to find H2. So we're just going to solve this formula here for H2 is equal to CP T2 minus T1 plus H1. Okay? So then we're just going to plug in our numbers. H2 is equal to 1.0045 kilojoules per kilogram times Kelvin. That's important. And then we're going to do that times, in these parentheses, that's important, in these parentheses, T2, which is 667 Kelvin minus 400 Kelvin. That's why we're able to get rid of this Kelvin so easily is because we're just multiplying it by temperature and canceling out the units. And that's going to be plus H1, which we're given in our problem, which is 400.98 kilojoules per kilogram. Okay. After you've plugged this formula into a calculator, unless you can just do it in your head because you're out of your mind, I applaud you. You get H2 is equal to 669.18 kilojoules per kilogram. All right, our problem's starting to take shape here. We're getting really, really close. We just need to find one more thing before we can find our work net per unit mass. So what we're going to do is we're going to do something similar to what we did in part A, where we used the formula we had and applied it to a situation that we have to find something that we need to know. And we're going to do it here using H3 minus H4 is equal to CP T3 minus T4. So we did the same thing just there that we did in temperature all the way back in the beginning of part A to find out what T4 was. So now we just need to solve this equation for H4. So that's going to be H4 is equal to H3 minus CP T3 minus T4. I'm not going to plug in all those numbers. That's a waste of your time. All that you need to know. And also, you're more than welcome to run those numbers yourself. I'm just lazy. Now, we know that H4, when you solve this, is going to be equal to 872.63 kilojoules per kilogram. Okay, so for our formula, we need H3, H4, H2, H1. We were given H3 and H1. We just found H2 and H4, which means that we have everything that we need to solve this formula. So, work net per unit mass is equal to, I'm going to write real big. That's too big. Whew. It's going to be equal to, our H3 is 1395.97 kilojoules per kilogram minus our H4, which we found over here as 872.63 kilojoules per kilogram. Don't forget your parentheses. That's going to be a minus our H2, which we found right up here at 669.18 kilojoules per kilogram minus our H1, which we were given in our problem statement as 400.98 kilojoules per kilogram. Okay, so now again, it's just a game of plugging it into your calculator, which I've already done that. I'm not going to waste your time. I know that this is 255 point, carried in 2 decimal places, 14 kilojoules per kilogram. All right. After all that, we have finally found it. So just to recap, we found our T2 first. We knew our CP, but if we couldn't find our CP, we have this cool little formula using our ideal gas constant to find it. And then we found our general formula. We took out, well, we solved for work net over M to get our formula that we actually needed. We solved for our extra enthalpies, and then we solved our equation and got our work net per unit mass. That's part B right there. Done. Okay, so we have just finished part B, and we got our work net per unit mass. We just have one more part, part C, and that's to find this weird thing. That is a Greek letter, and in this case, it stands for thermal efficiency. So, like I said, this is literally the easiest part of your problem. It's one formula with stuff that we already know from everywhere. It's literally going to take us 1, maybe 2 minutes. So thermal efficiency is equal to our pressure ratio raised to the 1 minus K over K. And that's it. That's really the whole formula to find our thermal efficiency. So thermal efficiency is equal to our pressure ratio, which we are given in our problem as 6 raised to the 1 minus 1.4, which is equal to K, 1.4, and that's it. And then once you plug this into your calculator, you get thermal efficiency is equal to 0.40, which is also equal to 40%. Just like that. See? It's really not that bad. It's the easiest part of this entire process is just finding that thermal efficiency. So that has been our Brayton Cycle practice problem. Thank you for watching and listening. And I encourage you to try this on your own and see if you get the same answers as me. Thanks for watching. Have a good day.